Okay, hello everyone. I guess we can start this talk. My name is Marcin Wielgus. I'm an engineer at Google, and today I'm here with my colleague Maciej to give you a deep dive into autoscaling in Kubernetes. This is the continuation of yesterday's talks, and yesterday we on SIG Autoscaling introduction, we discuss what autoscaling really is, why do you need autoscaling, how can you autoscale your application. More specifically, for application autoscaling, we mentioned about two options you may use. The first one was horizontal autoscaling. In horizontal autoscaling, you change the number of application replicas based on the current load. If the load increases, you add replicas, and if the load is decreased, some of the replicas are removed. Of course, you don't want to do it manually, and for that purpose, in Kubernetes, we have horizontal pod autoscaler that does this job for you. Horizontal pod autoscaler was covered in details yesterday, so we will not talk more about it. The other option to scale your application is to scale your application vertically. With vertical autoscaling, you increase or decrease the size of instances based on the current and past load. For quite a long time, there was no automatic support for this type of activity in Kubernetes. So the user had to manually specify the pod sizes and come with these good pod sizes in the first place. Luckily, this spring we launched Vertical Pod Autoscaler, which is hoped to set to make size setting automatically for you. Vertical Pod Autoscaler is not about reaction to the changes in traffic. One of the reasons why we started this project was that many users had no clue how to set pod size right, or didn't set it at all, or set it partially, or set it too big, too small. That was a huge problem for them. So one of the VPA goals is to help in this case as well. To explain how VPA exactly does its job, let's start with the API. The API is currently available as a custom resource definition and will probably stay as such for foreseeable future. This summer we had a quite extensive discussion with SIG architecture about whether to include vertical pod autoscaler in the core Kubernetes along with HPA API. This decision was made not that due to more complex nature of vertical pod autoscaler, it should remain to be developed as a kind of separate project, and for that reason the API will remain as CRD. At the very top level of VPA, it looks more or less like every other Kubernetes object. It has a name in object meta, it has namespace information. You can add labels or annotation to it, exactly as pods or deployments or replica set and other objects in Kubernetes. But more importantly, in a similar fashion as other objects, it contains spec and status. I will cover it right now. So let's start with specification. In specification, you have three fields. The first one is selector, which allows you to tell which pod you would like to have autoscaled. Containers with the same name in the pods selected with the selector will be considered as equivalent and will receive the same recommendations. The next item is the update policy. It will tell what exactly you would like VPA to do. The first option for update policy is to set it to off. In that case, VPA will only provide you with the information what the pod size should be. However, it will execute no action. The other option is to set it update mode to initial. In that case, the recommendation will be applied only to newly created pods, and the existing pods will be left alone. If you want to go full speed with vertical pod autoscaler, you can set update mode to auto. In that case, the recommendation will be applied both to the new pods as well as to the existing pods inside of your cluster. The third element of spec allows you to specify which containers should be actually affected by VPA. So there is a container name here. You can also specify what should be the minimum and maximum amount of resources that you want to give to individual containers. And of course, you can specify whether you would like this container to be autoscaled or not. Why is it important? Because you don't have to specify it for every single container in your application. You may use a wildcard pattern, asterisk, here. And in that case, you will be applying vertical pod autoscaler to all containers inside of your pods. If you're applying your VPA to all containers in your pods, you may want to exclude some of these containers from VPA. And for that reason, we have this field here, which can either be set to auto or off. And in off, the VPA will not provide recommendation or touch the containers mentioned here. So we know what we can ask a vertical pod autoscaler for. Now it's the time to show what VPA can give us in return in the status structure of the object. So in the status, we have two fields. The first one, conditions, give us information about whether the VPA is working at all. Has it provided its recommendation, or maybe it has not enough samples to provide anything meaningful to you. The other field is the recommendation itself. It starts with the container name, which tells you to which container this recommendation can be applied. Then we have 4 sets of number. The first one is relatively easy. It gives you information what should be the container size. The 3 others are slightly more complex. So lower bound and upper bound is the minimum and maximum amount of resource, minimum and maximum size of the pod that VPA is still considered okay. So if you are running VPA in fully automatic mode and the pod is within this lower and upper bound, it will not be updated. If it's outside of these boundaries, it means that the size of the pod is wrong and needs to be updated. The last field tells you what should be the pod size in the ideal case. If you didn't provide any constraints and there were no other obstacles, how much resources would VPA allocate to this particular pod? For example, VPA may think that the container in the pod should get 5 gigabytes of memory. However, in spec you put 3 gigabytes of memory as the upper limit. So in target you will get 3 gigabytes of memory. However, to give you information that the pod size should be bigger, this 5 gigabyte is passed here in uncapped target. And obviously, when VPA will be applying a recommendation, 3 gigabytes will be used. Okay, now hopefully everyone kind of understands what the API is all about. Let's see how it works in practice. Probably the most tricky part of this design is how we update pod requests. As you may know, for example, deployment contains history of the updates made to them. So if you update deployment, you change image or pod size, it creates a new entry in the history, which is basically a new replica set. Until a VPA gets a good grasp on the right size of the pod and containers in it, it may update the pods multiple times. We don't consider these changes important enough to go to the deployment history, which, for example, may have limited capacity. For example, it may be limited to last 9 entries. And if we updated deployment with every VPA change, we'll simply be polluting it with the unimportant changes, and important changes would be lost. So we also don't want to limit VPA to only a specific set of controllers, like only to deployments or only to stateful set. So we decided to go to a slightly different path than horizontal pod autoscaler and not to update any controller objects at all. Instead, we use admission plugins. The pod size is basically override during the admission phase. When the pod is created, it goes through multiple plugins, which checks whether you have enough quota to create, the pod, whether you have enough privileges to create the pod, or something else. In this change, you can also plug in your own plugin. In our case, we are plugging our VPA admission plugin, and this plugin checks all pods that are created in the system. Whenever there is a matching VPA object to the pod is updated and it gets the recommended size. Okay, now a little bit about the recommendations, which are obviously very important in this picture. The recommendations are calculated based on the observed real-world usage. For that, VPA recommender component periodically checks the usage of the pods that are under VPA. It gets the data from the metric server, recalculates the recommendations, and put these recommendations back into VPA status object, which I showed you a couple minutes ago. If you allow VPA to work in a fully automatic mode, it will try to update the pods. Currently, the only way to update the pod that is actually running is, unfortunately, to kill it and recreate it. So VPA constantly analyzes both set of VPAs and the list of pods. If some of the pods that are under VPA have requests outside of the allowed lower and upper range, VPA updater kills these pods and allows the pod controller to recreate the pod. And once the pod is recreated, it goes through the admission plugin chain and gets the appropriate size through the VPA admission plugin. Hopefully one day VPA will be more gentle to the pods, and if there is enough capacity on the machine that the pod is actually running, it may execute the in-place upgrades. Right now there is not an option, however, there are a couple of designs how to do it, and so hopefully in the near future we'll have it. Okay, so now a little bit about status. We are graduating vertical pod autoscaler to beta right now. What does it mean for you? First of all, it means that VPA actually works and does its job. While in alpha, it has been tested by a bunch of clients and their feedback has been applied to the product. Being beta also means that the API is relatively stable. We may change something in the future, however, the changes will not be drastic and they will be preceded with the appropriate deprecation period. It also means that you can slowly start using VPA in your production environment. If you want to do it, you should start using VPA in prod by running it in recommendation-only mode. Keep it in such state for a couple days and check whether its recommendations work for you. It is important that during this run, your pods get legitimate real-world traffic in the appropriate quantity. Otherwise, the recommendations of VPA will not be valid. You should also not blindly copy VPA recommendations from your test or staging environment because the amount of traffic in this environment may not match the real world. So this recommendation may simply be too small. If you are not running on GKE and you set VPA mode to auto, we strongly advise you to put size limits on your containers so that they don't go beyond node capacity in your cluster and in such a way become unschedulable. And obviously we recommend using cluster autoscaler with VPA because it may give you capacity when the pods grow. If you are on GKE, there is a bit tighter integration of VPA and cluster autoscaler and scheduler, and you may execute slightly less caution. That's all for VPA. You can find more information about how to install it and use it on our GitHub page, in our GitHub repository. And if you try it, please let us know what you think about it. And now it's the time for the second part of the presentation, the one about cluster autoscaler.
Yes, so let's talk about cluster autoscaler. So very quickly, we talked about it a bit yesterday, but it's the component that makes sure that you always have the right number of nodes in your cluster. So basically, if there is not enough space to run some of your pods, cluster autoscaler will add more nodes. If there are some nodes that are underutilized and can be safely removed, cluster autoscaler will remove those to save you some money. So Cluster Autoscaler has been in GA for over a year now, I think since Kubernetes 1.8. And currently it supports 4 cloud providers, Google Cloud Platform, AWS, Azure, and Alibaba Cloud. And hopefully there are more coming. So yeah, let's see how it works. And to talk about Cluster Autoscaler, we always have to start talking about the scheduler. So the scheduler is the Kubernetes component that decides which pod should run on which node. And for the Cluster Autoscaler, it's quite important how scheduler does it. So without going too deeply, but a bit deeply, scheduler has a process for deciding which node is the best fit for each pod. So imagine we have a new pod that has just been created and it needs to be scheduled. So basically there are 2 steps in the scheduler. The first one is the predicate functions. And those are sort of hard requirements of the pod, basically things that must be true for the pod to ever be able to run on a given node. So some example predicates would be, are there enough resources left on the node to satisfy the pod resource requests? Does the node match pod node selector or node affinity? Are all the pod affinity and anti-affinity rules observed? And so on and so forth. There is, I think, between 10 and 20 of those. And basically, every single predicate must pass for the pod to be able to schedule on a given node. So once we filter out the pods that cannot be scheduled, the nodes that cannot be used for a given pod, there is the second phase, and it's about priority functions. So those are the functions that basically rate each node to say how desirable it is to run a specific pod on this node, and then they are used to select exactly which node will be finally used. But I won't go into more details of priorities because we actually don't care about those at all in autoscaling. The important part is the predicates. So basically the way that Cluster Autoscaler works is it guarantees that for every pod there will be at least one node that passes all predicates. So there will be a node that makes it possible to schedule this pod. So that's one concept that's going to be very important in our thinking about Cluster Autoscaler. And then there is another concept, a node group. So this is specifically Cluster Autoscaler concept. And the node group is a set of identical nodes. So maybe all your 2 CPU nodes in the cluster will be one node group. And then your 4 CPU nodes will be another node group. And the way Cluster Autoscaler actually works is it resizes those node groups. So if it wants to add 2 more 2 CPU nodes to your cluster, it will just resize the corresponding node group and increase its size by 2. So with all those concepts, let's go into CA proper. So very quickly, what does Cluster Autoscaler actually do? So it monitors your cluster and it looks for pending pods. So the pods that cannot be scheduled because there is not a single node that passes all predicates. Once it finds such nodes, it actually simulates Kubernetes scheduler to see if adding some new nodes would solve the issue. If it would, it uses the node groups, it resizes the node group based on the result of this simulation. And there are a lot of misconceptions about Cluster Autoscaler, a lot of things that people expect it to do, which it actually doesn't do. So the node group is basically implemented on the cloud provider level, and resizing it just creates the VM. Cluster Autoscaler doesn't register this VM in Kubernetes, it doesn't configure it, it doesn't do anything with it. It actually, like the only thing it does is ask cloud provider for a new VM. And it just assumes that that will somehow result in a node being created. Another common misconception is what it looks at. Because it's based on scheduling, it doesn't actually care about resource usage. If you set your pod resource requests very low, and it's umming or it's burning the node, just using way more CPU than it requested, Cluster Autoscaler will not react because it's still schedulable. It doesn't impact scheduling. So for that sort of thing, you need pod autoscalers. And because of how tightly we're integrated with scheduler, we don't support any custom scheduling. So if you use that, then unfortunately you cannot use Cluster Autoscaler. And okay, so now let's proceed and sort of look how it all works now that we know what it does. And basically Cluster Autoscaler is made of 3 components. There is the cloud provider module. So that basically needs to be implemented separately for each cloud provider. And we currently have 4 implementations, as I said. And that basically is the implementation of the node group concept. So this is the interface between Cluster Autoscaler and cloud provider. So we have some common abstraction that we can use. The other part is the imported scheduler code. So the way we simulate scheduler is we literally just take and import the predicate code from scheduler. The good thing about it is any new feature that is ever added to scheduler is automatically supported by Cluster Autoscaler because we will just import it. The bad thing is it's actually important to run the version of the Cluster Autoscaler that is the same as the version of the scheduler that is running in your cluster. So what we do is we release new Cluster Autoscaler for each new Kubernetes release. So if you're using Kubernetes 1.12, you should be using Cluster Autoscaler 1.12. With 1.13, we will release Cluster Autoscaler 1.13, and so on and so forth. Okay, so I've been talking a bit about simulations here and there, and I wanted to quickly show you how this algorithm works. So imagine we have a bunch of pending pods that Cluster Autoscaler already noticed. There is one large pod and 2 smallish pods. And we need to decide how many nodes we want to add to help those pods. So basically what Cluster Autoscaler does is sort of greedy bin packing algorithm. We just see what would happen if we added 1 node. And we take the first pod and we run the scheduler predicates that we took from the scheduler. And we see what will happen. So in this case, the pod fits on the node, so we're all good. But there are still 2 more pending pods. So we try to schedule them as well. And now the problem happens because this pod won't fit anymore because the first pod basically took the whole node. So okay, 1 node is clearly not enough. Let's add 1 more. And let's see what happens then. The pod can schedule. Okay, so already helped 2 of our 3 pods by adding 2 nodes. We have 1 more pod remaining. We tried with the first node, doesn't work. Second one, it schedules. Okay, 2 nodes are enough. We can help all our pods by adding 2 nodes. Let's do that. And that's basically how Cluster Autoscaler works. I want to go into as much details on scale down because it's slightly more complex. But the basic idea is we also monitor every single node in the cluster to decide if we actually need it. And there is a bunch of criteria we use. So first of all, node is unneeded if the utilization is below 50%, or it may be unneeded if the utilization is below 50%. We may change this threshold in future, so don't get too used to the exact number. But another important criteria is that actually all the pods that are running on the node can be moved to somewhere else in the cluster. We once again use scheduler code and simulate scheduling to see if we remove these nodes, would all the pods be schedulable somewhere else. And finally, there are some kinds of pods that we are basically too afraid to touch, and we'll never remove a node that has one of those pods. So we don't touch system pods because restarting those can cause some sort of system outage. We don't touch pods with storage because or local storage because we're afraid that we may destroy some data. And we also have some specific mechanisms that allow you to say that pod should never ever be restarted by Cluster Autoscaler because of whatever reason you have to specify it. And with all of that, it's actually quite a complex thing. So I have a section about how to see what's going on with Cluster Autoscaler and how to debug it. And the first thing is we have this Cluster Autoscaler status config map. And it's basically automatically written and refreshed by Cluster Autoscaler. And it gives you the current status of your cluster as perceived by Cluster Autoscaler. So it describes how your cluster looks like, how every node group looks like, you can actually find what's the actual size of the node group, as in how many nodes there are in Kubernetes, versus how many VMs have been requested from cloud provider. So, for example, you can see that maybe some of the VMs haven't managed to start up successfully, and so on. And it also tells about cluster autoscaler operations. So, for example, in this case, you can see there is scale up in progress. There are currently 2 nodes, but cluster autoscaler requested 4 more nodes. So that's one thing that's quite useful to see what's going on with cluster autoscaler. Another things are Kubernetes events. We write a lot of those. So basically, whenever cluster autoscaler does a scale up, a scale down, basically any operation, there will be an event describing what just happened. So you can use those to basically trace the history of cluster autoscaler operations. Another useful event is basically we write events on pods. So if a pod was a reason for scale up, there will be an event saying that. If we restarted a pod because we did a scale down, there will be an event. And finally, there is an event that will be on the pod. If we see that the pod is pending, but we cannot actually find any scale up that would help that pod, that also will result in an event. So you can look for those if you think it's not working correctly. And more info is in our repository. There is all the code there. There is readmes separate for each cloud provider that says exactly how to run cluster autoscaler on each cloud provider. And we have a very extensive FAQ that sort of goes into why is cluster autoscaler not removing some nodes that I think it should remove, why is it not adding some nodes, and so on. So sort of common troubleshooting problems are covered in our FAQ, which is also in our repo. And I think that's about it about the cluster autoscaler itself. We once more invite you to join our SIG meetings, which are every Monday at 4 p.m. Central European time. We're very happy to discuss basically any feature request problems or anything else you encounter while using any auto-scaling features in Kubernetes. If the hour is not very good for you, or you just have some quick question and you don't want to wait until Monday, we're quite active on our Slack channel on Kubernetes Slack, so feel free to ask us any question there. And finally, thank you. If you have any questions, we'll try to answer them.
Thank you for the talk. 2 questions. First is for the first talk. Is there any conflict if we use horizontal pod autoscaler and vertical pod autoscaler at the same time?
Yes, there is a conflict. Basically, they are trying to do exactly the same thing. So if you are right now using HP and VP at the same moment, they will be trying to both, for example, increase the pod and increase the pod count, or decrease the pod count and decrease the pod size. So at this very moment, we don't recommend you using HPA based on CPU utilization and vertical pod autoscaler at the same time. However, if you point your horizontal pod autoscaler at custom metric, for example, at the number of QPSs, then you can use it. Because with HPA, you are guaranteed that, for example, you are passing only 100 QPSs to every instances, and then vertical pod autoscaler tries to adjust the amount of CPU and memory that is needed to handle this traffic worth 100 QPSs.
And the second question is, as far as I know, then the cluster autoscaler will only scale up 1 node at a time, right? No. Because in my use case, then I have an issue when the horizontal pod autoscaler they kick in for some services, and they need to add, for example, like 100 more pods. And then in the case that even though cluster autoscaler scale up new node, it will not be scheduled all of the pods, all of the new pods on the new node. And then the cluster autoscaler just stuck at that state. It cannot scale up anymore.
So I mean, I would have to look at like the details of the configuration, but in general, it does the sort of bin packing algorithm I described to decide how many nodes are needed, and actually it adds all those nodes in one go. So it resizes the like MIG or ASG or whatever you have behind the scenes by a given amount in one shot. There are some issues if you're using things like pod affinity that sometimes may cause it to add them one by one, but in general it should add them in like multiple nodes in one go.
Sometimes a second go is needed if we underestimate the need for the nodes. However, in most cases, only one scale-up is needed, and in one scale-up you will get as many nodes as you really need.
Mm-hmm. Finally, if you think it's not working for you, just tag us on Slack or something. We'll discuss that.
Hi, I have a question for the autoscaler. So you mentioned that, if I understand correctly, you put the scheduler as part of the library for the autoscaler and simulate the results as the scheduler. And the primary goal is to have reduce the scheduling pressure. Have you ever considered other design where you put this autoscaler functionality into the scheduler itself, or design a API between to consume the updates from the scheduler? Okay. I'm trying to understand the design rationale behind that. Thank you.
Okay, I can handle it. So historically, Cluster Autoscaler was started as a separate project because we didn't want to pollute scheduler code. So we want to keep Kubernetes core elements as minimal as possible and don't add functionality that may not be needed for all of the users. As you could see, Cluster Autoscaler requires some plugins to work. So every cloud provider that you want to use needs a special driver and all of the libraries. And probably you don't want to include all of these libraries in the default Kubernetes distribution and to the default code of scheduler, because, well, we have currently support for, I don't know, 30 different cloud providers, and all of them would want to be in the core Kubernetes. And for that reasons, we decided that we will have a Cluster Autoscaler running separately so that its scheduler remains relatively simple and Cluster Autoscaler can be developed at its own pace. In the ideal world, of course, it would be better if we didn't have to integrate, if we could integrate Cluster Autoscaler with scheduler. However, due to multiple reasons I described right now, it's not the best idea.
And regarding the API part, why would, because you could think that like one possible design would be for the scheduler to have some sort of a dry run mode. So the problem is we're not actually running against the actual cluster because we're adding those nodes in our simulation. So the state of the cluster changes. So we actually, what we need is to answer if the pod would be schedulable in some sort of fictional scenario where we have in-memory node objects. And then, I mean, first of all, that's not supported by scheduler that heavily relies on caching and other things that makes that difficult. And also, secondly, we run scheduler predicates a lot more than scheduler does. We run really a lot of those. And then the cost of serializing the whole cluster state and sending it to scheduler is just prohibitive.
We have been pinged that we don't have any more time for questions. If you have questions, feel free to ask them in the lobby. We are there for you, so don't hesitate to approach us. Thank you.
Thank you.